Thanks for this nice introduction and for the invitation to come to Munich. I just found out with Harald, I was here probably the last time they built this big laser in this big hall was around, and it was 19, what did you say, 98 or something like this, maybe. So I was in Munich since then, but not in here outside in Garten. So, well, okay, so I will talk about the quantum key distribution. Did I say something? Okay, it's better. Okay. As it's written here, state of the art, and I was not so quite sure how general I should be, how much I should go into details with this audience. I suppose most of you heard a little bit about QKD. So please interact and ask questions if I go too quick, or if I can try to adjust my level of detail I go into it. So you see that this the menu for today. So we'll start with some basic introduction on QKD and then talk about fiber-based QKD systems, and then a little bit how this we can go further in distance with thin field QKD, with quantum repeaters, with satellites. And then at the end, I will mention some recent work we do in Geneva on trying to making the systems more compact, faster, and also integrated in telecom environment. So this dessert, you know, it's always like in the menu, maybe where we are fed up already a bit early. We don't have to eat all these desserts, so maybe we can stop early if you see that. Okay. So, well, first, well, who knows about QKD? Half of people, roughly. Okay, even a bit more. So maybe we can go quickly through that. I think still it's important to remember what kind of ingredients we need in order to make QKD. Quite often you forget about that, no? So the important thing is that, for instance, you have protected offices on both sides. Doesn't make a lot of sense to encrypt the data if the offices are not safe, and that's already something which is not so obvious for users like you and me. No, you cannot protect your home. So for us, maybe QKD is actually not so interesting because the weak point is not the communication; it's already our office at home. So that's important. And then we have indeed this pointer is not so easy to handle. You need random numbers. Both sides, okay. Then you have a quantum channel, and then you have an authenticated classical channel, which means that, of course, Alice and Bob, they need to know each other, and they need to share already some secret beforehand they can start the communication. So that's important conditions we have. And then, well, based on that, well, this quantum cryptography, well, this is very, very basic here. The idea is that you exchange a key, and the eavesdropper would perturb this key, and then Alice and Bob can realize if somebody was listening to this exchange of a key or not. And now you can, this basic principle of using these quantum states, which are fragile and we cannot be measured by an eavesdropper without being noticed. That's a bit this principle, and you can now implement that in different ways with different protocols. And one protocol is this BB84 protocol. Maybe I ask again, who knows the BB84 protocol? Okay, almost everybody. So I can really go very quickly through this slide. So, well, if you know, it's, the idea is to encode the information, a bit, in a property of your, in our case, photons here. And one way to do this would be polarization. And you can say, okay, horizontal photon is a 0, a vertical one is a 1, and so on. But then you cannot do that with just a single basis. You need to add a second basis such that if an eavesdropper wants to measure, he does not know in which basis he should measure. And then if he measures in the wrong basis, he will introduce errors. Now, that's what you see here in this example here. Now, if, for instance, if let's say you have this incompatibility of a basis. So we can, at the end, only retain the states which were generated in a horizontal vertical basis and measure in a horizontal vertical basis or in a diagonal basis on both sides. So this means at some point you have to throw away half of the bits. So that you can retain only when Alice and Bob use the same basis. But it's important that Alice randomly chooses this basis and these states such that now an eavesdropper doesn't know how to measure, and we can see that what happens in the next slide. No, this is this idea that whenever you, let's suppose Alice sends a vertical photon, and now Eve well, she has no idea which kind of basis she should use to measure. So she can choose as Bob in the same way, randomly between a horizontal, vertical, or diagonal basis. And of course, if she uses the right basis, then of course she will get a right result and send this photon to Bob. And I only consider the cases where Bob also uses the same basis like Alice, because the other one we don't consider. And then it will be okay. And then in the other case, if Alice uses the wrong basis, then of course she has a chance, as you see here, a 50% chance to, well, she will measure randomly, or result will be randomly be a diagonal or anti-diagonal state. And now if she sends these photons to Bob, which measures in this horizontal vertical basis, of course, then there will be a random outcome as well. And then in 50% of the cases, he will introduce 50% of, he will introduce 50% of errors. So 25% of errors. This is the case when Eve makes this attack all the time, no? But more in general, you can say, okay, for this simple attack, Eve will have an information on the key which corresponds to twice the introduced error. No? Here she introduces 25% of error, but she will get 50% of information. And now what you can plot this information between Alice and Bob as a function of this error rate. So of course, if there is no error, mutual information between Alice and Bob, you can calculate that with this binary entropy function you see here over there, but you probably know that as well. So if an error increases, of course, Alice and Bob have to make some error correction and they lose information. But that's most importantly is here now, then if this error increases, also Eve increases some, the information of Eve increases according to the formula I just said before for this simple attack. And then in this range here, where the information between Alice and Bob is bigger than the information between Alice and Eve, in this range we can make key distillation, so we can reduce the rate to this called secret key rate, where we know now it's secret. So this means Alice and Bob have full information on that, but Eve, zero information. Okay, so that was known for everybody. So just very, very simple, just to remind this, sorry, to remind this different steps we need to make. So we send a lot of photons from Alice to Bob. Eventually, most of them will get lost, actually, have loss and detectors are not good. But from the one Bob remains, he will, of course, store them and announce to Alice what he got. This is this raw key, and then they have to make this basis reconciliation. You have to get rid of situations where we didn't use the same basis, which reduces again the key. Then this important step, they have to estimate the information of Eve, which is related to this quantum bit error rate, as I said. They make error correction, and then at the end, they make this privacy amplification, which again makes the key shorter, but now the key becomes secret. And then at the end, which is important again, you have to authenticate the whole exchange of information. course, Alice has to be sure that you really talk to Bob during this process. Okay, so that's QKD. Now that was quick, but I think since you heard already about that, was okay. Is there some question on that? Okay, good. Then you're really very smart, because normally people already start to ask, yeah, I know what happens if I'm okay. So that's good. We agree on that. That's okay. Now let's come to more of implementations and state of the art, as announced in the talk, or in the title. So this is the first experiment, which was done in 89. It was a free space experiment, no? Over 30 centimeters with polarizations. You see here Pockels cells, the laser source, and then a Pockels cells allows to turn the polarization, and on the other side you have another Pockels cell which switches the bases, and then a polarizing beam splitter. Actually quite a nice experiment, because it was already pretty complete with some analysis of errors and information and so on. And now the next experiment is one of our group, which was at the time the longest distance which was achieved for QKD in fiber. Now it's not in free space. And so we went from 40 centimeters to 400 kilometers in 20 years or something like this, no? Well, even more. And actually, it's interesting. It's not that it's a complete revolution. So in this very first experiment, the essential things were already there. So it was just a consequence of improvement of many, many things. So which is shown a little bit here. Of course, you need a very nice, fast emitter. You need a good protocol, which is resistant to some attack, as we will see. You good fibers, and you need good detectors. So it's, and just like you will maybe a bit disappointed, no, but it's the technical development, but also a theoretical development, because the first experiments which were made were not secure. So in the meantime, there was much more development on the proofs, and eventually we came up with secure keys at the end, really. Okay. So, well, just the first thing in this experiment, I just showed a slide, and it's actually nowadays most people work in fibers, not with polarization, but with what we call time bins. This means these 4 states which are prepared by Alice are not polarization states, but they are superposition of 2 pulses in an early and in a late time bin with different phases between. No? So you know this qubit sphere here. Yeah, indeed, I don't see the point. And then you can represent these 4 states on the equator of this. And the 4 different states depend on the 4 different phases. No? Okay. Okay, that's one way you can implement that. So you need an interferometer to prepare these states, and you have an interferometer at Bob also to measure the states, where we can change the phases. And then the first thing you can improve very stupidly, no? We have this 50% loss of due to a shifting, because we randomly choose one or the other basis. But now we can say, okay, eventually we choose always the same basis, and only from time to time we use the other one to check for security. But essentially we have one basis we use to exchange it. So we will not choose 50%, so make it more often. And then if you say, okay, we have one basis we use much often than the other, then maybe you can also say, okay, maybe we choose a simpler one. And actually you could say, okay, instead of having these 4 phases, we could just use a computational basis. So we have even the photon in an early or in a late time bin, and then just 2 other states on the equator. So if you see that on the next slide, you can use these 4 different states over here. Now we have a C basis we use all the time to generate the data, and then we have the X basis where we want to trick the eavesdropper. So the X basis is here to test if the eavesdropper is trying to attack. No, you see that very simple here in this, if eavesdropper wants to find out if it was a 0 or 1, well, she has to measure if a photon was in the early or in the late time bit. And if we send the X basis, this date here, for instance, then of course she will destroy, by measuring this time measurement, she will destroy the coherence between the two pulses. And that's what we find out then at Bob. No, if we send from time to time some light in this interferometer, if Eve makes a measurement on this time measurement on this X state, she will destroy the coherence, and we will realize that in the interferometer here. So we adjust the phases such that if no Eve is around, just one of these detectors will click. And if Eve interacts, all of a sudden the other detector starts to click, and then it's kind of alarm. Ah, Eve is here. That's the idea, no? So it's very simple to implement, no? Okay. Now, well, it's a kind of a parenthesis somehow, if you want. Normally, people, of course, we say, look, we have a single photon, no? And it's all this is very easy. And it's quite obvious that Eve cannot measure a single photon without this, whatever manipulating it. But we don't use single photons. So there's quite a lot of effort in the community to make real single photon sources. I don't know if some of you work on that. But in practice, it's just a nightmare. We are not really very performing. And that's why we use weak coherent pulses. And of course, if you use weak coherent pulses, we have a Poisson distribution of a photon number, and you may have more than one photon, and then, of course, it's no longer secure. A countermeasure to that is this decoy state method. So again, the question, have you heard about the decoy state method? Maybe it's a bit less. That's now more specific, no? Maybe a few. Okay, so it's quite important because that was really a big step to secure, because people used to use this weak lasers for all the time, but the only thing to do in order to make it secure was just to reduce the number of photons in the pulse, the average number of photons. But with this decoy state method, actually you can keep quite high average photon numbers and still secure. And I will explain you how it works. So that's why, well, first you have to introduce different values of intensities. That's why now we have mu1, mu2, mu3. Mu is the average photon number in a pulse. Okay, and the idea is the following. So as I said, now we have this Poisson distribution in this weak coherent pulse. So sometimes there is actually 1 photon, 3 photons, 0 photon, and so on. And you see here the probabilities to have n photon if you have mu photons in average. And of course, most importantly, the probability to have more than 1 photon, given you have at least 1, is not 0, it's mu over 2. And if you want to have mu quite big, then of course you have this attack possible. So what do we, so that is what the way Eve would make this attack. No, she will look what comes from Bob. She can make a quantum non-diminishing measurement. That's something she can do. I don't know how to do that, no, but she can do that. She can measure how many photons in the pulse without destroying whatever a phase or polarization or something. And then for her attack, she will concentrate on these photons, pulses which have more than 1 photon. So we'll take 1 photon out of a pulse and send it to Bob. So that gives correct detections and Bob and all information to Eve. Then, if she has not enough of this one multiphoton states, she can make single photons. She can send them without doing anything to Bob. Okay, that will give no information, but no error neither. Or she can try to make an attack. Or if she has enough photons, she will just block them. Because, you know, that's also, I didn't mention that, but Eve has, of course, she can replace the loss of the fiber with a lot of loss between Alice and Bob with her fiber with no loss. So she can reproduce the same amount of detection at Bob's with sending less photons because there's less loss. So she can concentrate on this multiphoton process. So that's what you see here. No, whenever this probability of a multi-photon pulse is higher than the probability of a detection, which includes the loss, then she can get the whole key. Okay, now a countermeasure to that is, as I said, you modulate these intensities. Okay, just by the way, that's also another important thing. If you have these different laser pulses, it's important that there is no phase relationship between the laser pulses. That's kind of a detail, but it's very important. If there is a phase between the laser pulse, this means Eve can make more powerful attacks. So you have to be sure that there is no phase relationship between the pulses. Okay, so you modulate these pulses, and now, of course, if you, for instance, you have now one pulse which has an average number of 0.2, another one 0.8. You see here the distribution. And of course, you see immediately that if now Eve sends only the pulses which have 2 or more photons, of course, the distributions are not the same. So that's the idea, no? Alice and Bob modulate these pulses, and then they detect all the photons and remember which kind of strength of pulse was sent and make statistics in order to find out if Eve was active or not, or making this attack or not. So what they do, in principle, for an infinity of number of intensities, mu1, mu2, mu whatever, you just measure the number of detections you got for mu1, for mu2, and so on. And this number of detections, of course, is a sum over the probability of having x photons or n photons in a pulse times the number of n photons events, the number of pulses which were sent. And then you add up all this, you measure this, and then you can actually find out at the arrival all the detections of half, if this was sent due to a pulse containing 1, 2, 3, 4 photons, and so on. And what you want to do at the end, you concentrate on the events which are due to one single photon. Because if it was one single photon, Eve obviously could not make this photon number splitting attack, and this is a part which is secure. So the secure key is then calculated with this formula here, and it's this single photon events -1 minus this error, this entropy of the error here. That is then the secret key which you can extract. Okay, that was a bit long intro in let's say parentheses, but that's clearly quite interesting or important to understand that we don't need single photons. We can weak coherent photons, and which can also be proven secure. And then if you have, normally we use, theorists suggest that we use 3 numbers, different intensities, and then you don't get the exact amount of a secret key length, but just a lower bound, which is good enough. And actually, we realized if you make finite key analysis, which is another issue in QKD, that you must make sure if you make the statistics now in order to determine the information of Eve, of course, you have to take into account that there could be some statistical fluctuation. So you have to make the statistics over a big block. And then also kind of take into account that Eve could be lucky and over a certain block and get some information. So we have to take that into account. But if you do that, it's actually good if you just use 2 average intensities. Especially you don't have a third one which is the vacuum, because this third one, the vacuum, of course, doesn't contribute to the key. So and it's a kind of a technical detail. But so at the end, to sum up everything, we have only 2 intensities. And then also one thing you can do in order to simplify, you just use one of the X states. Because as I said already in the beginning, we won't use the C basis to generate the data, the key, and the X basis only to check if the eavesdropper is active. And for doing this, it's enough if you just send one of these X states. You don't have to send both. So at the end, you see, we shrinked everything together. We have to generate just this 6 different states. So it's 3 states, different states at 2 different intensities. Okay, that's now the task that we have at Alice. And the way we do that, it's very simple. It's that we have a laser pulse, whoops, and which generates this series of pulses, laser which generates this series of pulses for random phase. And so we do that at 2.5 gigahertz, 400 picoseconds between the 2 pulses. We send that into an interferometer with a path length difference of 200 picoseconds. So now we have pairs of pulses separated by 200 picoseconds, which come out of this interferometer. And then we have an intensity modulator where we just can attenuate or completely attenuate the pulses. So we can, out of this pulses here now, we can carve out this pattern of what we want to generate these different states with just a single intensity modulator, which is also very convenient. And then we have some technical issues. Now we have to, here you see we have a filter to clean the spectrum of a laser. We have a dispersion compensating fiber because in order to limit the dispersion that at these high frequencies pulses after a long fiber don't spread out. And then of course overlap, go into a next time bin and overlap to a next time bin or something like this. And then this will introduce errors. Okay. Good. Is there a question on that, on this more tech experimental part? I'm happy to explain more if you're interested. No? Yeah. Yeah. Well, yeah, of course, she can decide not to attack, make her attack all the time. That's the first thing can do. But, and then she gets less information, no? Okay? And will generate less errors. But still, we will correct for the errors we see, and that will be fine. Important thing you should not forget, we make this randomly, of course. We check, we send X and C completely randomly. So it's not that we send C and then X a little bit and C and X a little bit, and she messages us. Yeah, that's really important, of course. And that's why this strategy will not work. If she will still, from time to time, measure an X state in her C basis and introduce the errors. No. Okay. More questions? No. Good. Then, well, okay. Now, well, this is just to give you now the ideas of the results you can get with this kind of experiment. Now we have, with these good fibers and so on, we see the key rate, which decreases, of course, as a function of distance. Note that this is a logarithmic scale, and this is this blue line we got. And we were happy at the time because we were better than the other points you see here on the graph. No, so we managed to get to something like 400 kilometers, no, with some reasonable rate. Okay, now the question is, can we do better? Well, first, well, all right. Yeah, here it's, I just add some points which, if what we get if we have the same kind of system, same kind of protocol, but now we have perfect detectors and everything is perfect, let's say. And you see, we will win a little bit, but wow, quite a lot, but not completely change the thing. And we will not, essentially, we will not go much further. So the ultimate limit is actually what this something which is written in this paper on this plop bound. You see the reference below. It's actually, well, of course, that's the limit what you can have if you send this kind of qubits or quantum information to a fiber. And it's not astonishing. No, it is essentially goes, of course, with the loss of a fiber. So we have this exponential decrease, or it's really not working this point. That's not, you see this exponential decrease here, no? And of course, you can go like this, you can go further and further, but of course, at some point, you're limited due to the noise and actually also due to the time of acquisition you want to make. So at some point, eventually, this is calculated here for 1 day. If you want to integrate more than 1 day, you cannot go further than, let's say, 600 kilometers, even if everything else is perfect. You're just due to the loss of the fibers. No? Okay. Now, now can we do better? And of course, asking the question is giving the answer, no, somehow. Of course, we can do better, of course. It's not easy, but we can try. And then, well, the first thing which came out a couple of years ago was this split field QKD, and you see here an experiment. This is the first experiment, it was 600 kilometers. And the idea is the following. Actually, you kind of cut in half a distance. So what you do, you have now 2 emitters, Alice and Bob, and you have a central station in the middle. And Alice and Bob send in this sequential light pulses to a center station. And the center station makes a measurement and announces if he got a photon. It's a little bit, it's inspired by this entanglement swapping scheme. Maybe some of you know, if you have entangled photons, you can send one in the middle and then make this Bell measurement. It's a bit this idea. So Ali, the guy in the middle, so this Charles, he could be also Eve. So she just says, okay, I got a photon in this detector on this detector, and this doesn't give him information what Alice and Bob did, but it announced Alice and Bob that this was successful. The result of that is that it's enough that the photon just travels half of the distance. So you can double the distance. Okay. And what actually happens if you can double the distance with this. It's a simple idea, but experimentally it's very, very complicated because now we have a 100 kilometer long interferometer we have to stabilize. That's really a challenge. But well, people managed to do that. Ah, okay. So this is a very recent experiment over 830 kilometers. It's not by accident that it's twice this 400 kilometers I showed you before, no? And well, maybe I don't go into much details unless somebody is really interested in that, because there are different challenges. No, we have to generate these 2 lasers on both sides, which are coherent in phase. And for this, you send a laser from a center station to the outside station, where you use, you see that on the next slide here. And then you have this local laser here, and you make a homodyne measurement between this seed, or this, not even a seed, this reference laser which comes, and you can adjust, have a feedback on the phase on the laser. And so we get 2 lasers which are in phase. And then you modulate these lasers and then send everything to a central station. So well, anyway, I'm happy to explain more in detail, but you see a little bit the idea. It's a very, very complicated experiment. And then you have to have a feedback, of course, stabilizing the length of the fibers and so on. But nevertheless, you see the results are very nice. So this is actually the orange points here. That's the 2 points from our paper, our last 2 points. And now this is this new work, this blue line, blue points here, and the others are earlier twin field experiments. And now the feature of this twin field is that you double the distance, or you kind of reduce the loss by 2. And you see that here, no? You have this plot bound, this limit, this straight line here, this black line, with a certain slope, which corresponds to the loss of the fiber. And now with this twin field technology, we can reduce the loss, and you work on the other slope. That's why you can beat this plot bound, no? And eventually can go up to 800 kilometers. Okay, that's very nice. Now you can still ask your question, can we even do better? And I don't know how much time I have, 10 minutes maybe, no? Okay. And there are 2 approaches, no? One approach is, he's not happy for some reason here. Oh, sorry, I have to go out here. Works again. Okay. I had some interference with some other program which was still open. So one idea is using a quantum repeater. And the quantum repeater, the idea is that you work with entangled photons. You have many, many links. You cut your total link in many, many parts of links. You distribute entangled photons on these subparts, as you can see on the top line. And then you put the photons in quantum memories all along. And there are people working on quantum memories, or used to work on quantum memories. And then once we have these quantum memories filled with these photons, you can make entanglement swapping. So entanglement swapping is this, what I mentioned before. Now we can make a common measurement on 2 photons. And then, depending on the measurement result, you can generate an entangled state on the other photons. So this means that if you have this entanglement swapping here, then you all of a sudden have entanglement between here and here. Okay, and then you repeat that and repeat that, and at the end you end up with entanglement between very extreme stations, and you can use that to generate a key. And of course, the scaling is better than a direct transmission, no? So then it goes with just with a transmission on a single short link. Okay. That's one way to do. Well, the problem is that quantum memories, it's a lot of effort done, but it's not so easy to make very good ones. And this is just to give you an impression that you have all these experiments. And as long as you stay in this kind of orange region, you cannot beat a direct transmission. So it's very hard to do better than a direct transmission. Then what people do, they use this trusted repeaters. No? That's what now this is this Euro QCI or quantum communication infrastructure. That's what is built up also in Germany, I suppose. Not in Switzerland because we are not part of Europe anymore. But then there will be this link all over Europe, and it will be based on a construction like this. So you have just point-to-point distributions of key, and then you have to trust the repeat in between, and to make the an XOR of a key, and you transmit the keys like this. So of course the bad thing is that the bad guy can sit in the middle somewhere and listen to a key. If you can protect, what you can do, you can make different paths so that the bad guy has to control all the paths, but it's still, you have to trust this. It's just not ideal, no? Okay. The other solution is satellites, and you know that Harald is working a lot on that, no? So I will be just show you the possibilities. So one is The best one would be that you have this entangled photon source on the satellite. You send one photon to one ground station, the other one to the other ground station. And then again, you can establish a key by making measurements on these two photons. And the good thing is that in this case, the source has no information. So the source has no information at all. So you don't have to trust the satellite. That's why it's written over there, untrusted. So this is an experiment by a Chinese group. The problem is, of course, you can imagine, no, we have to send at the same time, both photons have to arrive at the ground station. So the total loss is very big. And this, you see here, the average coincidence rate is in the order of 1 Hertz. So it's only during 275 seconds both ground stations see the satellite at the same time. Then you have to wait for the next turn. No? So under these conditions, they showed a violation of a Bell inequality, but they could not extract a secret key with applying finite key analysis. No? Then much easier is that if you have just a satellite which is going around the Earth and you exchange a key between the ground station and the satellite, and a bit later between the satellite and another ground station. But in this case, you have to trust the satellite again. No? Okay, that's the thing. And then you see here, then the rates are much higher and have kilobits. And you can indeed exchange a key. So you see here the satellite, which it's at the horizon, it is far away, and then on top it's a bit closer. So the rates increase, and then it goes on the other side, and it decreases again, and so you have this maximum of key in the middle and low at the end, and you see the errors generate here. So that's very nice. Okay, and here I try to summarize a little bit all these different possibilities. Well, I don't want to go to detail. I don't have the time, but yeah, essentially, it's a quantum repeater would be very nice. No, we can just the rates, even if it existed, will be very low. That's a bit disappointing. Even if you are very, very optimistic on the efficiency of the memories and so on, the rates with the known protocols are very low. And the disadvantage is it doesn't exist. Yeah, no. And then we have this untrusted satellite, which actually also have very low rates, but at least it exists. The trusted repeater is kind of obvious. The trusted satellite is less obvious, but at least you can make worldwide QKD. It's very expensive. No, the price, don't look too much at the price. It's just kind of estimation. And then this twin field, which this new, relatively new technology, of course, it's a little in between. So it goes to 800 kilometers. So it's already quite reasonably good. Okay, so is there a question on that? So that was kind of state of the art of QKD now, and now I have another 5 minutes to give our latest developments on what we do now. That will be very short. Okay, so that's what we now work in, or are on these practical issues. No, as I said, faster detectors and smaller and cheaper, whatever. So we have seen that before. Now this is this curve, and we have two limitations. In distance, this is related to the noise of the detector, and in rate, this of course related to the speed of a detector. So now our experiments, they saturate at short short distance because detectors are not fast enough. So in order to go faster, we worked on detectors, and we worked pretty much on this superconducting detectors. And well, again, I cannot go in too much in detail, but the idea is you have a superconducting wire. If a photon hits this wire, the wire heats up. And if you let pass a current through this wire, and you can detect this heating up because it introduces a resistance, and you see a little voltage peak you can detect. That's the detection of. You see this hot point, and then you have to wait, and then it cools down again, becomes superconducting again. You see the performance of the detectors. It's very nice. Now we can have up 90, this is really a typical performance. Normally people say typical and it's the best, but it's really typical. Because it's an older measurement, in between you have better ones. So it's, you see, it's 85%, but you can go to 95 or something like this as a function of this bias current. And the blue curve is the error rates. And you see this, error rate, sorry, the dark count. And if you don't do anything, it's kind of 1 kilohertz. And actually it turns out that this dark count, it's on the next slide. Okay, sorry, just in between this, they have a very nice jitter. They have a very small jitter of, in best case, 26 picoseconds, which is important for our QKD. If the jitter is too big, then you may have detections in the adjacent time bins, which generates errors. And as I said, the dark count is actually dark count, which is not really dark count, it's actually detection of black body radiation. So in order to get rid of this detection, you have to filter it with a filter which is cold inside the cryostat. And you see that here. So if you have no filtering, you have this curve. If you filter, then you go down to 1 hertz. You can even go below 1 hertz of dark counts. You see it in the different filters, and you can go well below 1 hertz. Then you reduce a little bit the efficiency because this filter introduces a bit of loss. Okay, but then you would like to go faster. And the speed of this detector is a bit different parameters, but the main parameter is actually the inductance of this meander. So if you want to bring back the current into this meander, it takes some time to do this inductance. So one way to reduce that is to make shorter meanders. And the one way to make shorter meanders is to split this surface, which is adapted to the size of your fiber, in many sub-segments. And then you can increase the speed, no? And then we make different kind of detectors like this. You see one with 8 pixels and 8 with a single electrical output. This allows you to measure the number of photons actually you have in the pulse. So we have a photon number resolving detector, you see, and then the signal depends on the intensity, depends on the number of photons which are detected at the same time. That's quite nice for some fundamental quantum physics experiments. But we are not interested in that. We are interested in the speed for this QKD. So we have here a detector which has 14 different wires, and they are read out also 14 times. So we have 14, you see that here. So you have, well, here first you see this layout here, oops. And this, you see the diameter fits roughly the size of your single mode fiber, we just put on top of that. And you see that on the other picture over there. So we have this ferrule where you come in with a fiber. Then inside we have this structure here, and then we have this pad where we can connect these different pixels to the wires which go out of a cryostat. No? And now by doing this, you see we can go to quite high count rates. At some point, of course, if you have lots of photons, then wires are inactive, and then the efficiency goes down. But you see now you can go up to 10 to 8 counts per second, or even below, above, and at some point the efficiency goes down indeed, and the jitter increases a little bit, but still it's very reasonable. And now doing this, we have this relatively recent results for QKD, and you just have to look at the last number to make it simple. So you see now at 10 kilometers, we can go to 64 megabits of secret key rate, which is kind of a best value you can do now. And even over more than 100 kilometers, we still have 3 megabits of key rate. So that's really a bit the state of the art now of this QKD with this kind of detectors, which is not very practical enough, because I said practical issues, of course, a superconducting detectors is not so good. So if you really want to go to a commercial system, then it's maybe not a solution, but maybe you don't need this high rates, but anyway. So for more of a commercial thing, the challenge is to shrink our setup, which is a picture of this other setup I presented, in a small chip. No? And that's something we also did quite recently. So you see here a picture of a chip at Alice on the left side. This is silicon photonics, which has a couple of advantages. First, it's very standard. It's very small, and it can integrate also electronics, which saves us a lot of money because the electronics is very expensive at these high rates. And if you can integrate that on chip, there are no good light sources in silicon photonics. That's why the laser is still external. And then on Bob's side, we cannot use silicon photonics because it has a lot of loss. So we use this femtosecond machined glass plates where you can essentially put the interferometer on it. No? That's because we have this interferometer. That's really an amazing thing. No? On this silicon chip, you can have an interferometer which has one path, has a couple of millimeters length. No? We just wind it around many, many times, but it's pretty cool. And well, this is the results we get with in-gas APDs now, not with superconducting detectors. But what we have to retain from that is just actually that the results are really comparable to that what we have also in a big system. Okay, so as promised, I skip the last part of the dessert, and I come to my conclusions. So you see a bit the performance you can achieve nowadays with QKD, this 800 kilometer with this thin field technology, or the 400 with SNSPDs, or 300 with InGas. As you've seen, the secret key rates are the order of more than 50 megabits per second now. We're now constructing a prototype with this PIC, with this integrated chips. It's not yet finished. Eventually, it would look a little bit like this, I hope. And another last part, which I didn't mention, now, if you combine this quantum channel with classical signals on a telecom network, it's of course, we have a lot of challenges with crosstalk, with strong signals and Raman scattering and so on. And this limits then the distance to something like 100 kilometers. If you want to go more further, then you, as I said, well, quantum repeaters, unfortunately, that's still quite far away. And a secure satellite communication is, I say, for the rich. Well, it's actually, I say for the rich, of course, it's for the rich, no? But also QKD is for the rich, no? We don't have to care about QKD, no? Nobody cares about our bank account with a few thousand euros on it, no? So of course, for the rich or for powerful, even you have your own satellite or you have governments, but for us, to be honest, don't need that, no? But I make this joke for the rich because in some of my talks, I present our efforts in satellite communication for the poor. And the satellites for the poor are drones. So we started some activities with drones and so on. But I will not talk about that. I just let me stop with this nice picture from a satellite communication for the poor, where the satellite is actually not even on a drone, but it was at this, we had made some link. It's over there on the mountain. And we had this link from some place close to Bern to this Jungfraujoch in the mountains in Switzerland. Okay, thank you very much for your attention.
Yeah, thanks a lot for the nice and very clear talk. Are there questions, please? There is one.
Thank you very much for this interesting overview of many different activities. No? I was wondering, I mean, everything you explained was basically starting from Alice sending single qubits. but you could encode the information, let's say, in a big ensemble of qubits, a complex entangled state, whatever, and send that. And then maybe overcome the need to have a repeater, but instead do everything on many photons and error correction and so on that would be involved. So it's not easy. But I was wondering how you would compare these two approaches.
Yeah, where two, yeah, that's of course people go in this direction. There is one way is still staying in this kind of classical QKD scheme where, but not instead of sending qubits, you can send high dimensional quantum states, QDITs. And this allows you to send with one photon more than 1 bit of information. No? So that's appealing in some way, but probably it doesn't change a lot in terms of performance in distance, for instance, because if you have QDITs, for instance, if let's say you have time bins with many time bins, of course, for this single photon, you have then many occasions to have a dark count on all these time bins. And this kind of limits you at the end also. So that's not so interesting. And it's also more complicated to implement that, of course. But and then another approach is instead of having this classical quantum repeaters I showed here, where you have single photons and then these repeater stations, you can do like something you said. You can have a cluster states to send big amount of quantum states, and then you try to make some kind of, you lose some of them, and then to make some kind of error correction, actually in a quantum computer, and then send them further. So there are approaches in this direction, but it's still quite far away. Yeah.
You think it's even more further away than the repeater approach that you showed for single photons?
Well, depends to whom you talk.
I'm just wondering how you would compare the two approaches, and
I'm not.
You think in the long run is maybe more.
Promising. I don't know, Adrian, if you want to say something about that, but our quantum memory guy in Geneva, Michael Afzelius, if you're talking about the other approach, he says, no, it will never work. Arguably, the other guys say the enormous quantum memory approach will not work neither. So I don't know. I think we can agree that both approaches are still far away from some practical realization.
So we have one online question, right?
Yes, we have a question from Stefan Diadamo, or Stephen Diadamo. Do you believe hollow core fiber will make a big improvement on QKD systems? If so, which improvements do you predict?
Well, hollow core fibers, no, of course, in principle, they could have less loss than classical fiber because light is propagating essentially in air and not in glass. But I don't know the latest numbers now. It's still, the loss in hollow core fibers are still much higher than in normal fibers. Another advantage of hollow core fibers could be that they can guide much more wavelengths, different wavelengths, and you could have multiplexing, wave multiplexing. So that could also be an advantage. But you can already also, of course, multiplex with normal fibers in many different frequencies, and you can win on that, but it's still a linear gain. No, you have 10 systems with 10 different wavelengths on the same fiber. I think will not completely change because it's too far away from really very nice performance. So it will not completely change gain.
Yeah. There's another question. Yes.
I was wondering, has the photon number splitting attack been implemented experimentally, and what would be the challenges?
Well, not really. I think, well, you could try, but it will be so lousy that it doesn't make a lot of sense to try to imitate an eavesdropper. We know he has unlimited technology. It doesn't make so you just calculate it and you do. On the other hand, where are people hacking, attacking QKD systems, but not on this level, more on the detector, where there's different attacks on the detectors. You can blind the detectors and manipulate the detectors. That's on another level, no? Because this photon number splitting attack, it's something, it's very clear. You know our system, we can calculate the information Eve can get and so on in the best conditions. And it's easy to model and it's under control somehow. The other attacks on this hacking, it's actually different. So in the model you normally have on the QKD, you make assumption on the detectors, they behave like they should behave. And these other attacks are more interesting in some sense because they force you to adapt your model you have on your detectors and admit that, no, in practice, not everything is like in theory, you know. See what I mean? It's a kind of different story. But implementing photon number splitting attacks is, you know, we can try to separate this. If you have a 2-photon state, no, we can, of course, we cannot make a photon number measurement without destroying the state. But you could put a little beam split which couples out a little bit of light, and then you could measure the light coming out there, and you can repeat that and eventually cut or not pass. But it's also horribly bad. It will not be better than just a simple beam splitter attack. So it's not worth to try to do that.
I was wondering, how would you compare the continuous variable QKD in comparison with your discrete variable QKD? So are there any advantages?
Yeah, indeed, I didn't talk at all about CV. Well, I think there are a couple of advantages. So if you read the papers of the CV guys, they always have in the introduction their advantages, of course. And what they say, we don't use single photon detectors, which is, admittedly, it's a bit our problem. So that's an advantage. They claim that they are more resistant to interference with classical channels. So if you implement them in networks, the last pass I skipped. And well, the results we got in this recent experiment kind of contradict that. I think we are as good as CV. So an advantage of CV could be they could be faster at short distances because we are as you have seen, we are limited with our count rates of detectors. They don't have this problem. A disadvantage, they are much more sensitive to loss. So they cannot go that far. And but this key distillation is a headache. It needs big computers or whatever, and yeah, you see, it's a bit. I think it eventually probably both systems can live together for different use cases, whatever, and it's not clearly that one is much better on all domains.
Okay, thank you.
We have another question here, or do we have maybe one online? Maybe you can say a few more words about. So you said it's for the rich. Do you think it will stay like this, or do you think it might change, or under which circumstances? If what could happen that it changes?
That's interesting. Of course, it's a cliche. If I talk, I should not say it's not only for the rich, because I know that Harald works on his handheld devices. Eventually, everybody will go to the teller machine and get money with that. To be honest, I don't believe too much in this. And I already mentioned a little bit, for me, the issues for, well, to be honest, QKD is interesting for, first of all, for long-term security. If it's just for short-term, I think it's less interesting. So it's for long-term security, which concerns us as well. If it's in the domain of health or something like this, maybe that's something that should be protected. So that's maybe some. So that's the first thing. And then the second thing, I already said that. No, I think for normal citizens, which is actually, well, first of all, you cannot protect your home. You cannot and you share your data anyway with everybody. So it's not the fact that you sometimes communicate some things, data that maybe with imperfect encryption that is really threatening you. I think the threats are elsewhere. And I even think that for normal people, to guarantee the democracy, what's more important than encryption is actually is steganography. You know, steganography, that means that you can communicate with somebody, that nobody realizes that you communicate with this person. And if you think about the political situation in many countries, that's really very important. No? But if you're in, I should not mention the country, but you can imagine, no? In some countries, the mere fact that you communicate with somebody can bring you a lot of trouble. It's not about encryption or whatever, just the fact that you communicate. And if you want to organize some opposition in a totalitarian country, you need to communicate. And so you need to find ways to communicate, to organize yourself, that the others don't realize that. And this is about steganography, you know, and there are techniques to. We also made an experiment on quantum steganography at some point. And I think that's much more interesting than cryptography, because it's not for this purpose, no, for. Okay.
Is there maybe another question? Yeah, I see one in the back.
So experiments with trusted repeaters are not as hard as with quantum repeaters, right? So,
Yeah.
when do you expect? So do you plan on conducting experiments with trusted repeaters?
No, well, let's say for a physicist, it's not very interesting. No, it's kind of just aligning many links, and then of course you need some key management and stuff like this. But that's so in our group, or we don't plan to do that. And this has been done now anyway. So in China, they have this famous link between Shanghai and Peking, where they have this trusted repeater link.
So that would be the way to go with quantum communications in general, but not something as secretive as key distribution.
Yeah, it's well, it's yeah, you have to. Well, it's not as well. If you assume that the nodes are secure, no, you trust them, then it's the same like for QKD. No, it's still QKD in this sense. So, but you have to master these nodes. And so, if I say QKD is for a rich, no, it goes actually in the same direction. No, you can a government, or what you know do now in Europe, you can control kind these different nodes, and you can do that. A big company can do that. Maybe banks, they have enough of their different banks all over the country. They can make this secure network. But of course, for users like us, it's not very secure, no, not at all, actually. No.
All right, thank you.
Any more questions? I don't see any. So then let's thank Hugo again.
Thank you.